just called this New Avenues of Data Science in Official Statistics, because I think that lots of things could be said about this, about the importance of data science and machine learning and statistics and official statistics. I'm going to touch in some of the issues. I'm not sure if I'm going to cover them all, but maybe I'm going to focus on those that are most important for my role now, and those for which I know that something is being done, at least in Statistics Portugal, and also something that is being made at the level of Eurostat. Okay, so my first slide is this one. In very small letters. I hope that you can read them, but it was on purpose. It's like those letters that you write when you receive some letters from your bank. Is that the views expressed in this seminar are those of mine and do not necessarily reflect the official positions of Statistics Portugal. I have to make this disclaimer before continuing. So that's it. So this is the contents of my talks. I'm going to start with a little notice of two cross-cutting issues, as Steve McFeely indicates. Then I will proceed with maybe the most part of my talk, big data and official statistics, where I'm going to focus the most part of the applications. Then administrative data sources, trusted smart statistics, and finally, maybe a little point on training and education for official statistics. Okay, sorry, I don't know. Okay. So maybe I'm going to start by the end. So maybe this could be, I was hesitating before the start if this could be the last slide, because I'm talking about the future. But indeed, I decided to put it in first, because this has been published in a paper by Steve McFeely, who is now the chief statistician in an institution inside the United Nations. And you remember that in 2013, the leaders of the European statistical system published the Scheveningen Memorandum, where they identified the potential for compiling official statistics from big data. And this is maybe one of the biggest challenges for official statistics now. Imagine what we can do, or what anybody can do, and actually they are doing it now, if they use streaming and flow and can compute dynamic statistics with that. And maybe some of them can be derived from administrative data. This is, by the way, very, very difficult and costly, but on the other hand, it offers the potential for more policy relevant and outcome-based statistics. So, as McFeely said, there are two cross-cutting issues in the future role of official statistics. One of them is literacy, and the other is interoperability. So I'm going to just give you a very, very brief first introduction of literacy. Maybe you know what we're talking about. You're talking about statistical literacy, which is something that is essential if future economies are to work efficiently, and if you want to take the citizens inside the institutions and also outside in order to contribute to society. And I think that everybody, at least in official statistics, realize now that it is very important to consider the role of the national statistical offices in this kind of education more actively. So I'm not going to talk more about literacy. This is it. And the second issue is interoperability. And interoperability has to do with maybe the most part of things that I'm going to address today. Let me start with something that I found out very recently, which is this notion of fair data. So this has been published by a very small group. We call it the Fair Data Group, and FAIR is an acronym that stands for findability, accessibility, interoperability, and reusability. So this is an European Commission expert group that published this report that you can see in the right side of your screen in 2018, and that it gives data greater value and enhance their propensity for reuse, either by humans or by machines. So this is not only about the data, this is not only about technology. This FAIR group focused also on the research, on the researchers and the research culture in terms of data sharing, in terms of the the practices and principles that we need to deal with metadata standards, tools, technological infrastructures, and so on and so forth. So this is very important, and it touches all the, I would say, the actors, the stakeholders that deal with official statistics and with statistics in general. So if you want to take a look at the report, you can just click on the link that you can find on the right side. So the main recommendations from European Commission in terms of data, and as I said before, this is not only about official statistics, this is about data in general, is that we need to professionalize data science and data steward roles. This is very important. And also, of course, we need to train researchers, for them to use data properly and to share the data, even the data that they produce, of course. So in terms of these recommendations, I could put them together like data science and data stewardship. Data science skills are those that are related to handle, process, and analyze data to draw insights from it. You know that. We are going to talk a little bit later on about data science. In what concerns data stewardship? So data stewardship is something that ensures data that are properly managed, shared, and preserved both throughout research life cycle and also for long-time preservation. So data stewardship has to do with the managing of data. Okay, and so that's why it's very important that this FAIR group, that's why they also focused on this role of the stewardship, because we know, everybody knows that not all researchers, I think that most parts of people that are listening, that are attending this webinar now are researchers, I would say, and we know, we are aware of that. Not all researchers should be expected to become experts in data science or data stewardship. So if they come, for instance, if they go to the Safe Center in Luxembourg, where the headquarters of Eurostat are, we know that they need some help from data professionals. So it's very important to know that we should build research teams that should be also supported by or include those data professionals that have this kind of skills. And this is really a challenge. Okay, so now I'm going to enter in the second point in my webinar is big data. You know, big data is something that you are listening to almost every day in almost all the conferences and expert groups in Eurostat and in the European Commission as well. You know that we can say that big data is something like the ubiquitous collection and availability of data, and big data is everywhere. We are now in the third task force, third ESSnet, the European Statistical System Network of big data. So there are lots of projects related to big data. And let me frighten you a little bit. You know that big data has to do with this new concept of datification. And datification is something that takes into account all aspects of life and turning them into data. This is really scary. Let me give you some examples. I think you know them all. Facebook datafies personal networks. Sensors datify all kinds of environmental conditions. Smartphones, you have maybe one inside your pocket, they datify personal communications and movements. And also wearables, this is maybe not so common, but this has to do with the Internet of Things and something that you can wear. They datify the personal conditions. So if you now, you take a look and imagine what kind of things you can do with this datification in the world, you know that Hal Varian is the senior researcher at Google and very famous economist. Together with Choi, 8 years ago, they used Google queries in order to help predict economic activity. And they proved that economists, the investors, the journalists, the media, the decision makers, they heavily follow monthly government data releases on economic conditions. And it's not very difficult to use this kind of information, you know. By the way, a few months ago, Statistics Portugal published an indicator on population mobility at regional level based on Facebook data. This has to do with data for Social Good Initiative from the University of Chicago and also for Nova University. And this brings us room to start what some call the official statistics 2.0, which is a great challenge because this invites us to enter in the new era of statistics, what some call the second wave in official statistics. Okay, but everything is so good, but of course that big data brings big problems and very, very big headaches. And these are, according to David Pfefferman, I would say only some of maybe the most important issues that I'm going to cover today. So coverage and selection bias, data accessibility, new legislation, privacy and data protection, disclosure control, computer storage, techniques of computation and data analysis, record linkage, data manipulation and stewardships. And I'm going to focus on these 4 topics today. I'm going to start with the first one. So what are the main problems of big data when it concerns the coverage and selection bias? So I just talked a few minutes ago about this ESSnet on big data. If you just Google that, you will find there is a huge project with several different tasks. I'm also participating. Me and not only me, some colleagues in Statistics Portugal are participating in this project. In particular, I'm dealing with this credit card transactions, what they call the financial transaction data, FTDs. And so maybe you realize, if you have just read this first sentence, that big data based on credit card transactions contains no information at all on transactions that are made with other means of payment. So this is very limited if you based yourself and your analysis only in credit card transactions. On the other hand, if you base the opinions of the population in social networks, you also realize that these opinions are different in principle from the opinions that are held by the general public, because there are some people that just don't use social networks at all. So one first, maybe very important, maybe one of the most important issues is related with this coverage and selection bias. And this is maybe the most important question. Will random sampling continue playing an important role in processing big data? We will see that. There are lots of projects that use big data to answer some of the questions. For instance, some researchers try to predict the consumer price index based on maybe you know that, Billion Prices Project. This is data that are freely available about prices all over the world that are collected by, I think that they are collected by Google now. Is this possible? Is this realistic to use this BPP to predict the CPI? Is this also useful and scientific and rigorous to predict employment using online job advertisements, or for instance, using satellite images to predict crops? So of course, this is very limited. We have this coverage in select bias, but maybe we can use proper statistical analysis to identify and test the prediction models, and use new algorithmic estimators and try to overcome these limitations. I'm going to focus now in one of these examples. I'm going to use these satellite images to predict crops. And this is something that we have already done in Statistics Portugal some years ago. But my first example is not from Statistics Portugal. It will be from the ONS, the Office for National Statistics of the United Kingdom. They used as an experience aerial imagery to recognize the number of caravan parks. So there were publicly available Google aerial images of UK addresses, and then they used machine learning techniques to detect residential features of interest. You know that there are people that are living in caravans. When you make a census, you have to count on them too. So this is a very important way of counting people, or at least counting caravans, because you don't know if the people are inside or not. Of course, we are only measuring the shapes of this kind of let's call it residences, the households, if we can call it like that. And then in terms of statistical methodologies, several classification methods have been used to detect caravan parks, like Gaussian naive Bayes, logistic regression, support vector machines, and random forests. In the case of Statistics Portugal, we have used a different example based on one project called LUCAS, the LUCAS project. LUCAS stands for Land Use and Land Cover Survey. So this is an European survey, a very expensive one, based on satellite images. And then the idea is to classify this territory in the European Union. You see the image here in the first map, the green map, based on almost 1 million different sampled points. So all of this is made using the Inspire grid, and then we have 1.1 million of points. And then the idea is to classify the territory, the land cover, using one of these 1 to 10 different classes, like arable land, permanent crops, grassland, woodland, shrubland, barrelland, artificial land, that stands for buildings, routes, highways, and so on and so forth. Inland water, transitional water, and well, the last class is that impossible to photo interpret. So this is something that is done in two different phase samples. The first part is based on orthophoto interpretations of satellite images. And then the second part you can see below is based on field collection of and interpretation of the territory when people are there. Like what you can see here, you see these are and this is an interviewer. So this is a person that goes to the field and just identifies what type of class in terms of land cover is that. So based on those satellite images, this is a 3-by-3-year project, the LUCAS project. And the idea was a pilot survey, because this survey is very expensive, there was made an attempt to the European countries, to the member states, to see in what extent they could use their own data set, their own inside information to produce the results for the land cover instead of using the Lucas project. Because in fact, this is not very representative of the territory. For instance, you don't have, if you want to have any kind of representativeness of the territory in Portugal, for instance, imagine that you want to estimate the area in terms of square kilometers of arable land in the, let's see, in Alentejo, for instance. This is not possible because this data is not representative at the regional level. It's only at the European level and that's zero, I mean the country level. So we try to use small area estimation to improve the quality of the estimators. And for that purpose, we used auxiliary information based on the farm structure survey and also the COS, the land cover chart produced by another institution outside Statistics Portugal. So this is I would say, the basic scheme of a small area estimation. You know that you have different types of stratas, and then you have different kinds of samples. And this small domain, imagine that this area here is the small domain. So, of course, that in this case, the small domains or the domains represent the geographical units. As I said, Alentejo, for instance, it can be considered a small domain. In order to use small area estimation models, there are different kinds of estimators. And we can classify the estimators overall in two different types. The direct ones, which are the ones that are used the most part of the times. They only consider the information that is collected by the service and not and only for the time period under analysis. And on the other hand, you have the indirect estimators and also the model-based estimators that take observations of the variable of interest, as well as other information outside the space and the time of the domain. So this is an example of a direct estimator. This is not the most common one, the Thomson Estimator. This is one that has been derived by Martino and Palmieri explicitly for this Lucas project because it measures the proportion of the area. And this is this is estimator, and below you can see also the variance of the estimator. And this was a direct estimator, and now we have an indirect one. By the way, there are two here: the EBLUP and the CBLUP estimators. So the EBLUP is an estimator for which the S of the CBLUP considers the spatial component. And they have been based on the famous Fay-Harriott model. And this CBLUP has been particularly developed by John Rao and Isabel Molina. And this is something that you can see here. And maybe if you take a look at the papers, you will see the developments. And these are the results that, I'm sorry, because the headlines are in the titles of the table are in Portuguese. This is at the level of the classification of the land. You remember from the first slide, A, B, C, D until H. At the NUTS 3 regions like Alentejo or Trás-os-Montes or something like that, you have the estimated area based on, and you can compute the difference in percentage between the one that has been modeled by the chart of land cover, the COS 2007, and the small area estimation methods that we can use only based in the Lucas data. So this is not a huge difference. And which is more important is to compute the CVs, the coefficients of variation that gives you a fantastic idea of the precision of these estimators. And so you can see that these CVs, they are measured in percentage, are between 4% or even lower than that until 12. I can say that these are really low values. 10% or even 15% for a coefficient of variation is not so huge. So another application of small area estimation for land use and land cover has been done by Suel Mapina and also by Arminda Manuela Gonçalves, together with me in a traineeship in Statistics Portugal. We just presented this last year using the farm structure survey, not the Lucas survey in this case. And so we have explored more estimators, and even this direct estimator modified by regression, and also the CBLUP and eBLUP. And these are the results. And it is good to conclude that, for instance, the CBLUP and eBLUP, they present greater gains in precision when the sample size is larger, and also when the correlation between the dependent and independent variables is greater. So, by the way, the dependent variable that we are estimating here is the amount of area, is the area inside the regions, the area for each particular type of land cover classification. And of course, that the CVs are higher when the regions are lower. So, in terms of sample size, if you find a region like Baixo Alentejo or even Alentejo Central, for which the sample size is very low, then the CVs are very high, which is something that we would expect to happen. A third application that I consider here, still in example 2, although this is a completely different thing, has been developed by Soraya Pereira and also Ferdinand Putman and Luis Correia. That has been published in the journal of, not in the journal, it has been published in another paper. I'm sorry, you can find it in the bibliography. It was published in RevStat, yeah. It was published in RevStat in 2018, and the field of application was different. So the idea was to apply small area estimation to measure unemployment rates. And they used also small area estimation, but together with different kinds of models, because you know that in this case the dependent variable is a binary variable, to be or not to be unemployed, and then also they have used an unemployment rate using a beta. They modeled the unemployment rate using the beta model, and also a multinomial model. And they found out also some results that you can find in the issue of RevStat in 2018. Now for the other topics, privacy and disclosure control, which are also very important. I'm going to focus a little bit on that and see that there are two kinds of big data. And maybe you are aware that some big data, although it is big, it is identifiable. And if it is identifiable, it means that a person or company can be identified, either directly or indirectly. According to an European directive, every kind of data that has to be published by official statistics, even if it is collected by the concept of the big data, has to be anonymized. So the data must be stripped of sufficient elements such that the data subject can no longer be identified directly or indirectly. And this is more or less the typical flow that we follow from the data source until the pseudo-anonymized data. And of course, here you can see the algorithms for statistical disclosure control, where you can measure the trade-off between the risk and utility, and this is really our challenge. So I'm going to introduce the third example, because we are now researching on the protection of the next census 2021 data in Statistics Portugal. So please take a look at this paper from Inês Rodrigues. We are developing a framework. We are based, of course, in something that the other countries are also doing, because this is based on the harmonized protection of census data in the European statistical system. And we are using, or maybe the methods that have been elected to be used are two different methods. There are both perturbative methods. It means that the data is going to be changed because there are also other types of non-perturbative methods where you can just hide the values or aggregate columns, but the data is not changed. But here you are going to use perturbative methods of two kinds: the pre-tabular, because they are applied to the microdata before producing the tables, or post-tabular, when they are applied after the tables are over the tables. And in particular, we are going to use these two methods: record swapping and the cell key method. Let me start with record swapping. This is a pre-tabular method, as I said. And you can see more or less how it works, although this is only a schema. Imagine that, because this is a geographical method between pairs of households that you can exchange. Okay, we're talking about households and people. We're not talking about companies here, because we're talking about census 2021. And if you identify some households in the geographical space with characteristics that are very, very similar, then you can exchange. You can exchange this data. You can exchange the households. So this is the principle of record swapping. Now for the cell key method, which is a little bit more complex. It has been developed and applied in the Australian Bureau of Statistics, and it's going to be usually applied in the. It's already been applied in the census for the countries that have the census this year. So it starts with assigning each record a random number. So you have a record and a record key. So that's why this method is called the cell key method. So you can have a different key, a different code, let's call it like that, for each different record. So imagine a flat database with registers and attributes. Each record will be assigned a record key. But then when you aggregate the table and you get, for instance, 4 females, this table is aggregated by age and by sex. If you have got 4 females within this age group, so 4 means that you have number 4. If you sum up all the values in the table, and if you realize that they sum up 162. So let's imagine that you take the last 2 digits and the cell key will be 62. So now for the cell value 4 and the 62, it means that the perturbative value that you are going to use to change the original table is going to be +1. So this is what we call a macro data method, because this is applied to a table. This is a post-tabular method because this has been applied after the table has been compiled. And then the new value after changing this 4 into a 5 is this here. What is one of the main advantages of this method compared to the previous ones that we have been using for decades is that the random noise is added for each table in such a way that the same cell is perturbed always by the same value. So you don't change the values every time you have to increase to add some kind of random noise. Only to proceed with this paper from Inês, there are some risk measures that you can compute, like the relative change on the number of cells with lower frequency, because this is the most problematic cells in the tables, the ones with lower frequency. Also the proportion of cells with frequency lower than 3. You can also compute some utility measures like this absolute distance and relative distance between the original table and the perturbed counts. Don't forget that, as I said before, this is a risk, this is a trade-off that you have to take into account between the risk of identification of people and households and companies, and also the utility of the data, because we want to keep the data useful for everybody. So these are the utility measures that you can take into account. And at the end, we have used this in some hypercubes. So the hypercubes are the data from different countries, and apply this in different scenarios. So you can see that these are the RS stands for the record swapping, and CKM is for cell key method. And well, we reached the conclusion that the results suggest that in general, the record swapping provides higher utility while the cell-key method results in higher protection, means lower disclosure risk. So, in terms of big data and official statistics, of course, there are lots of problems. You know the problems. The problems that are not only related with the protection of data, on the privacy issues. There are other kinds of problems. I'm going to focus on some of them, like the first one, big data and big errors, the cleaning, the combining sources of data, and the problems of stability. I'm sorry, I was going to move for the next slide because I thought that there was another one here. Yeah, in terms of big errors, this is one of the problems that we have in big data, because sometimes you don't know what the true value here is. You see, so there is a lack of consistency when you are using the same concept in different files, in different data sources. So this is one of the biggest problems in big data. Another problem has to do with processing data in terms of missing data, outliers. Another one is this one here, combining sources of data. When you have to combine different sources. Data stability, when you have modeling techniques in terms of longitudinal data. What about if the data just changes? What about if the owner of the data just changes the concepts? What can you do with that? So there are lots of problems, but there are also some possible solutions for that. So now I'm going to move to one of my final topics, the administrative data. Because we are using administrative data, by the way, usually I would say in official statistics in Europe. And so what is administrative data? This is data that are reported by administrative authorities for legal compliance, or it comes by recording decisions made by administrative authorities, or even if it is generated by authorities to support planning, implementation, and other kinds of politics of policy. So the main advantages of the use of administrative data now in official statistics are the decrease of costs and burden in terms of the data that is collected every day from companies. You know that we are sending service to households and to companies. With taking this opportunity of using administrative data, of course, that you realize that we can decrease the costs and mainly the burden of this kind of tasks. Also, we can increase the data availability, and which is, in my opinion, one of the most important issues, we can raise the quality of the output produced. Okay, and also in comparison between different countries when you need to do this kind of comparisons. But the main challenges, also, of course, you have challenges on using administrative data are. I have identified those three here: transform administrative populations into statistical populations, transform administrative entities into statistical units, and also transform administrative variables into statistical variables. So you have also problems with missing data, outliers, and so on. So let me give you some examples of using administrative data in official statistics. One of them is the Dutch population housing census. So the CBS, the Central Bureau for Statistics in the Netherlands, they used a macro integration of data coming from the national accounts, trying to change the macro data into micro data. And this is a technique that is often used, the macro integration. In Portugal, we are now editing and making some experiences with data from Social Security. So we are using the information of the monthly statement of remunerations coming from the Social Security. This data has some kinds of problems like missing values and problems of missing data. So we need to input data. So the original data contains about 100,000 companies, and approximately that leads with approximately 4.2 million employees. The idea is that in the future, when this is the information at the employee level is available, we can use it in Statistics Portugal. But now we are using the information at the level of the company. So we have made some work by using support vector machines to make imputations for missing data. So basically, we have elected the companies to be imputed, which are those that have more than 9 employees and with at least no data in the previous month, and also based on other criteria. And then we have implemented a support vector machine algorithm that, well, pretty much it worked very well. And these are one of the outputs. So I'm not going to enter in detail here, but I can assure you that by using some measures of precision, it works very well. The rate of success of this algorithm is about almost 100%. Finally, my last point, I'm almost ending now, is the trusted smart statistics view, this trusted smart statistics perspective. It has to do with, well, some people say the future role of official statistics. So the idea is to augment the capabilities and the role of data beyond the mere generation of input data, and also include some degree of processing, like data streaming processing. And this is a very common slide that everybody is now sharing, because you can see that every day you are generating data from your mobile phones, from the surveys, from the administrative data, from big data in general, and you can combine all of this for policy, for media, for research. So this concept of trusted smart statistics is somewhere in between. You can find it here, between the processing of this data and trying to integrate this data in the classical official statistics. Let me give you an example. For instance, the mobile network operator data that can be used to extract spatial temporal statistics about, for instance, where people are and where people move from and to. So I'm talking about the mobility, from the day-to-day mobility. And of course, it brings us lots of challenges, like, for instance, the problems related to the privacy. But these problems, we think that they can be solved in terms of potential risks of data misuse against the individual, because everything is being decided with the operators and together with the civil society associations, the consumer associations, advocates of civil rights, and so on and so forth. The mixed mode surveys. Okay, I forgot that this is also a point here. You know that during this COVID-19 outbreak, we had really, and we are also now facing some problems related to the personal interviews, namely the CAPI and the PAPI modes. So the idea is to, so I should have finished now. The idea is to involve combinations of different types of modes, like having dual frame sampling. But this at the same time brings us some challenges, like the non-response increase, the change in non-response nature and characteristics. And this is the big question, how to deal with this change. Let me just recall that these are the main modes of interviewing, like the CAWI, online interviewing survey, the CATI, the telephone survey, the PAPI, which is completely outdated nowadays. We don't use it anymore, at least in Portugal, the paper personal interview, the CAPI, the computer-assisted personal interview. This is more or less a face-to-face interview by using a tablet or a table computer, and then you have also the CASI, the computer-assisted self-administered interview. So, according to some researchers, the main problems of mixed modes, and we are facing some of them nowadays, is that do respondents provide the same answers to questions that are asked through different modes? And if it is not the case, how can this problem be minimized? Can we simply combine answers obtained from different modes? So there has been some research using, for instance, the ICT survey, the Information and Communication Technology survey, and they have used these different modes. And this is a table that gives you an answer of what people use. You can see, for instance, that most part of young people use CAWI, but they don't use PAPI anymore. So the response rate of older people for ICT purposes, when you need to use a computer, is much worse for people, for older people, than for people under 26. So you answer differently according to the interview modes, which is this is a very concerning problem, and we are now focusing also on this kind of things. So the idea is to use mixed mode surveys. There are different rules of thumb that you can use, and also, of course, using calibration methods towards fixed levels, like the age, the level of education, for instance, or sex, and things like that. Okay, so I think I'm going to stop now. I had a last point on training and education, but I can give you this slide, I think, because it sums up everything that I was going to say. In my perspective, these are maybe the most important skills that someone has to have nowadays to be a part of this official statistics community. And that's it. Thank you.